Well, today we're going to look at autoencoders and representation learning, transfer learning in the second lecture. But this one will be specifically about autoencoders. I'm going to start by explaining what autoencoders are. So basically, they are neural networks that learn to output the same as the input we give them. But then I'm going to explain why we should use what we can use autoencoders for and what usefulness they have. And we'll see that this all boils down to how we constrain the inner part of the autoencoder, so the encoding of the data we pass through the network. So we'll see different ways of imposing these restrictions on the encoding, undercompleteness, regularization, noise, and so on. And then we're going to see some applications to manifold learning and to the image generation or data generation and so on. So let's start with this basic idea. So an autoencoder is a neural network that we train in order that the output of the network, so what we have over here out on the outside of the network, the data is passing this way, the activations, this output is the same as the input. Inside the network, in the hidden layers, this innermost layer is learning a way of coding the data, the examples that we gave it, in order that the example can still be reconstructed on the second part. So we can think of the autoencoder as divided into two different parts. The first part is an encoder that is mapping from the input into this latent space, this hidden layer here that will represent the input in some encoded manner. So we can imagine that this encoder is converting pictures of cats or whatever into vectors that have a specific encoding for those images. And then we have the second part, the decoder, that takes those codes as input and transforms them, maps them back into the original input space where we had the images. So the autoencoder, when we train an autoencoder, we are basically training these two networks attached to one another. One to encode our data in some way with some properties. We're going to see that in more detail. And the other one at the same time to decode it back into the original space. Now, this basic idea, we can represent it this way. The encoder is some f function of the input. The decoder is some g function of the hidden representation of what is encoded. And basically, we're going to train to obtain our input from the combination of g applied to f. So after decoding our encoding, we get back the original input. This is one big advantage that we can see immediately here is that we don't need labeled data. Since the target of our network is the same as the input, all we need are the features. We can just put in whatever we want. We don't need to have anything previously classified or labeled, and the network still learns. So in this sense, even though the mechanism for training itself is the same as we have seen, backpropagation, minimizing the loss function, so it works from the perspective of the network as if it was supervised learning. From our perspective, it's unsupervised learning because we do not have to supply any labels for our network to learn specific targets. So this is a big advantage with autoencoders in that they can learn from unlabeled data. The question is, why should we want to train a network to give us back exactly what we put into the network? So this is the tricky part here, that this can be useful if we force the autoencoder to do something that we can use in that internal representation. So that latent space has some properties that we would like to have. For example, it can have a lower dimension than the original data. If we can squeeze the data into a lower dimension and still have an encoding from which we can retrieve the original data, then we are capturing some structure of the data and projecting it into a lower dimension without losing much information. So in general, we may want to capture some structure of the data, maybe for data compression, for feature selection, something like that. But this may not be always with lower dimensions. I'm going to show you other examples, but the main idea is that we want the autoencoder to do something useful to the data. So usually autoencoders are feed-forward networks. You may create, for example, recurrent autoencoders and something like that. Since you're going to look at recurrent networks further on in the semester, I'm not going to talk about that here. But in general, most autoencoders are feed-forward networks. And since the target is the same as the input, we can teach them without labels, so they work as unsupervised learners. The thing is that we need to force the network to do something useful to the data. So there must be some bottleneck there. Otherwise, if we just have a network that has the layers of all of the same size or something like that and is free to do whatever it wants, then it will simply just copy the input to the output and we will not have anything useful inside the network. So you need to force the autoencoder to do something useful, and then from that we may extract good features even without supervised learning. We capture some structure of the data, and we're going to see more about this idea of capturing features and reusing them and creating a good representation of the data. We're going to proceed with that line of thought in the second hour. But this is also a fundamental idea for autoencoders. So let's see different ways of creating autoencoders in order to squeeze some knowledge out of the data, even with this kind of unsupervised learning. One simple way of doing this is to use an undercomplete autoencoder. An autoencoder is called undercomplete if that hidden representation, that hidden layer H here, is smaller than the input X, which is also the output. So if we are forcing the network to reduce the dimensions when it creates the representation of the data, we are using an undercomplete autoencoder to squeeze that data into fewer dimensions. So basically, we just have this loss function that compares the input to the output of the autoencoder. Remember that the output of the autoencoder is the result of first encoding our original data X with some function f. This is the first part that encodes and produces this hidden representation. And then we decode it back with the other part of the network, this function g, and we compare this to the input. So we are penalizing the differences between the input and the decoding of the encoded representation. If we use a linear autoencoder, so we don't have nonlinear activations, we just add one hidden layer with linear activations and just do a linear combination of everything, autoencoder converges to something similar to principal component analysis. But if we have nonlinear transformations, then an undercomplete autoencoder can learn a lot more powerful representations because it's not restricted to a linear combination of the original features like we have in principal component analysis. There is, however, the danger of overfitting. There's always a danger of overfitting. It's a bit strange to imagine how the autoencoder could overfit since it's only trying to reproduce the same data that we input into it. So at first thought, we could think that there would not be an overfitting problem because it's not trying to generalize from that data to other examples. But actually, that's the whole point of training the autoencoder, is to try to find some kind of structure in the data that we can really generalize for that kind of data. And it's easy to imagine an extreme example of how an autoencoder could overfit. So suppose you have a very large autoencoder network that receives input of a very large size. So each example X here could be a very large vector, but compresses everything down to a single value. So the encoder outputs only a single number. But if it's powerful enough, it could store inside the combinations of weights in the network all the possible examples. And so the decoder will simply take that number as an index and output the corresponding example. And this would work like a table where you have, if it's example 32, then it's this output. If it's example 33, it's this other output, and so on. And it would not generalize anything. So it would not be useful in capturing the structure of the data. So for autoencoders, if you're using them for any kind of serious work, you should always also consider the same kind of problems of validation, of checking overfitting, and so forth. So we can squeeze the data. We can do that by creating the encoder and decoder. We always have these kinds of problems of avoiding the danger of our model being too complex for the data and overfitting. Let's see an example here. This is a classical example of an autoencoder. Here we have input values. There are we can imagine this as a one-hot encoding of 8 different inputs, and we can use 1, 0, 0, 0, or 0, 1, 0, and so on, like this. And we train the autoencoder to output the same thing. And inside, in the middle part of the network, we see these different combinations of zeros and ones. We only have 3 neurons here, and we see that the autoencoder is learning a binary encoding of these 8 different values. So by the 8 different combinations of zeros and ones here. The reason why we may want to do this is to learn the manifold of our data. So the concept here of a manifold is a set of points in some possibly higher dimension that is homeomorphic. I'm missing an E there. It's not homomorphic, it's homeomorphic to a Euclidean space. So basically we can map it so that that set of points locally in the neighborhood around each point works like an Euclidean space. One example of this would be the surface of the Earth. This is a diagram of seismic events on the surface of the Earth, and we could represent these seismic events with 2-dimensional maps around each neighborhood. We cannot really spread out the whole surface in a 2-dimensional map without tearing anything, because if you look at the world map, then if you go out one side, you have to go back the other. But for any neighborhood around any point, we can draw a map, and this approximates quite well to a 2-dimensional space. So this is the idea of a manifold, is that our data may not be, even though it's in a higher dimension. For example, here we have coordinates in 3 dimensions. The data itself may be laid out in a way that could be represented in a lower dimension while still preserving the same kind of structure in the data. And this is the kind of things that we may want to learn when learning the manifold, how to represent this data into 1 dimension or 2 dimensions without losing this kind of structure. And this is one of the things we can do with, for example, principal component analysis. But principal component analysis would not work well, because you're only looking at the variance and then only doing linear transformations. So it's not as able as nonlinear methods to really find the correct manifold for the data. So this is one thing that we can do with autoencoders, and this is actually an example that you can do in the tutorial today. This is the banknote dataset, the one that we used in the first tutorial, and this is an example of using an autoencoder of this architecture. So we have 4 features going in, then we have a layer of 6 neurons, 4, 2, 4, 6, and then 4 features going out again. And we train this without regarding the different classes. We train it with just the features for the whole data set, and the autoencoder learns to project the data into these 2 dimensions, preserving a lot of the structure. So this is what you get from the autoencoder. And when you look at the different classes of the banknotes, the real banknotes and the fake banknotes, you see that they are pretty well separated in this projection. Whereas if you do principal component analysis, you get something that is very much mixed up, because you're only looking at variance and not trying to capture this actual structure of the data. And further on, these autoencoders can do transformations that are a lot more complex than a simple linear transformation. So basically, with autoencoders, if you use undercomplete autoencoders, it's very simple to learn a manifold for the data. And this works because we are pushing the network into doing two different things. First, we want the network to reconstruct the input from the encoding. So it will encode the data and then recover the input from that encoding. But at the same time, we are also forcing the network to do this under some constraint. For example, we are forcing, in this case, the network to rebuild the four-dimensional data of this data set, but after encoding it into only 2 dimensions. So the encoding must be in a way that the network can recover the original information. And by pushing it in these 2 ways, we can force it to capture something about the data that is useful. But undercompleteness is only one way of doing this. We can do this in different ways, for example, by using regularization. An overcomplete autoencoder is one that, it's the opposite of the undercomplete one. It's one where the hidden representation is actually larger than the input. If we just do this and we force the network to this network to output the same as the input, nothing useful will happen, because this allows the network just to copy the same values from one side to the other and give us the same result trivially. But we can impose some constraints by restricting how that hidden representation can be with regularization. So with some change in the loss function or in the way we train the network, that will force the network to go in a different direction than just copying the values. For example, with a sparse autoencoder, we can try to force the network to recover the input without having too many activations at the same time. That is, our hidden representation, our latent representation in the network cannot have too many values different from 0 at the same time. For example, suppose that we want to coerce the network, to force the network into having a lower probability of any one neuron from the hidden representation being active for the same example. And this p hat here is the probability that we estimate, that we measure on each example, which is simply the average activation of our neurons. So if the average activation is 0.1, this means that 0.1 of our neurons are active on average at the same time. So now we're going to train the network in order to minimize the loss between the input and the output. So this is just the same thing we've been using with the undercomplete autoencoder, but we're going to add a penalty with some small regularization factor here, lambda, and this penalty is the Kullback-Leibler divergence. So remember, we saw this a few weeks ago. This is a measure of the divergence between different probability distributions. So let's assume that this is a Bernoulli variable which has a probability of being on or off. This is the probability that we are measuring on our hidden layer, and P is the target probability. So suppose we want as a target only 5% of the neurons to be active at the same time in the hidden layer. So we penalize any deviation from this 5% target. And so the network must at the same time try to minimize the loss function here and try to make it so that on average the number of active neurons in the hidden layer is as close as possible to that P probability that we are imposing. So if we are using, for example, sigmoid activation in the hidden layer, then we can get this sparseness just by having very small activations. But a sigmoid activation can only actually be 0 if we go all the way to minus infinity in the input. But if we use something like rectified linear units or something like that, then we can actually have zeros in the hidden layer, and these may end up corresponding to neurons that are simply turned off, and we use only a few neurons at a time. This can also be, so we can think of this as having some prior assumption on what would be the probability of using those features in the hidden space. We can imagine that that hidden encoding has a set of features, and each example can only have a few features at the same time. And if we imagine that we have some prior probability distribution for the number of features in that hidden space, for example, this probability P with a Bernoulli variable, or for example here with the Laplace prior, so this would be the distribution for having a certain number of activations here. This is the absolute value for any activation. So we have a probability of some neuron being active, and we can consider this added up for all the neurons in the hidden layer. So in this particular case, if we use this probability distribution, when we do this kind of thing, the divergence between the desired distribution and what we actually have in our data, in our network at some point during training, what we get is this simple regularization term where we are adding to the loss, the original loss function for reconstructing the input, we are adding a term that is the sum of the absolute values of the activations of the neurons. So this is analogous to what we saw as the L1 regularization, but note that we are not applying this to the weights as we did in that kind of regularization. We are applying this to the activation of the neurons in the hidden layer. So basically what we're doing is we're forcing that hidden representation, the encoding, to use few neurons at a time, which leads neurons to specialize into particular tasks. So this is an example of a sparse autoencoder, which was trained on images that are 10 by 10, so 100 input values, grayscale images, and the hidden layer is also 100 neurons for the representation. So we are not imposing that constraint where we are using an undercomplete autoencoder that is forced to represent the data into fewer dimensions. But we are imposing sparseness constraints. So for each example, only a few of these neurons must be on at the same time. And what happens is that different neurons specialize into different patterns in the images. So these represent for each neuron, these are 100 neurons here, for each neuron, what image normalized maximizes the activation of that neuron. So this neuron is sensitive to this kind of contrast on diagonals. This one is sensitive to this other kind of contrast, and so on. So in this way, we are not reducing the number of dimensions that we use for the representation, but we are identifying useful elements, useful patterns in our data for which these different neurons become specialized. And this is one usefulness of using sparse autoencoders. This is an example, so you have the reference to the paper here, a comparison of training sparse autoencoders on NIST, so that database with the handwritten digits. These are 25 neurons in the here represented, and you see that if we don't impose any sparseness penalty, the neurons don't really specialize. They have these different patterns, but they seem to be all mixed together. But with different penalties, L1, L2, T-student, this Bernoulli, Kullback-Leibler divergence, and so on, you always see that different neurons are specializing in different parts of the shape of the numbers. So this is something that we can do with the sparse autoencoders, specialize the neurons to identify particular patterns in our data. Another way of training an autoencoder, of forcing the autoencoder to find something useful about our data, is with the denoising autoencoders. So what we're doing here is we are using the same loss function. So this is the loss function is just a comparison of the output as it is and what it should be. But the difference here is in the input. We are comparing the output, so the output of our autoencoder, with the original image, for example, these two. But what we are giving the network is a noisy version of the image. So we take the original image, we add noise, we pass it through the network, and we compare with the original image. This means that our autoencoder must be able to figure out what kinds of changes in the image were noise and what corresponds to the actual pattern of the data we have there. So this is one way of forcing the autoencoder to be less sensitive to perturbations in the input and create an encoding here that has a more robust and smooth manifold for representing the data. So with denoising autoencoders, the algorithm is simple. You just have this autoencoder network. It outputs the same as what the input should be. But when you are training, when you sample an example from your set of examples, you apply some corruption function. For example, you can apply normally distributed noise to the inputs with some small fraction, or randomly deactivate some of the inputs. This would be this kind of example. We randomly put some pixels at white here, and so they get changed at random with this noise. But the exact kind of noise, it depends on what we're doing, and there are several possibilities. But the idea is basically the same. We create some corruption on the original image, and then we feed this corrupted version of the data into our autoencoder and minimize the loss with respect to the original image. So we force the autoencoder to give us back the original image without the random noise. A different approach that is related to this one is the contractive autoencoder. So here we have the loss function at the same time. So this is the same loss function reconstructing the example x from x itself. So this is x, this is the output of the autoencoder, and this must be as close to 0 as possible, the difference between the two. But we also add a regularization factor here with some weight lambda, that is the sum of the squared derivatives of our hidden representation with respect to the inputs. So basically, we are computing how our hidden representation is changing as a function of the input, the derivative here, this nabla, and we penalize our autoencoder if these derivatives are large, and we force the autoencoder to learn representations that are robust, are less sensitive to small perturbations in the input. So this can favor smaller weights, and if we were only using this term here for the optimization, it will simply, everything would go down to 0 or to a constant, and the derivatives would be 0. But since we are also forcing the network to be able to reconstruct the original data, then we have this trade-off between the two things. And what happens is that the network learns to create these reconstructions without being too sensitive to small perturbations in the input. And the result here is that this is something similar to denoising autoencoder. You can imagine that denoising autoencoder makes the whole network less sensitive to perturbations in the input, because we are giving it small perturbations in the input and forcing it to map to the same original image. Contractive autoencoder makes the first part, so the encoding itself, less sensitive to perturbations in the input by forcing the derivatives of the hidden representation with respect to the input to be small. And the reason why this is contractive is because we are forcing the encoder or the autoencoder to map different slightly different inputs into the same region, into the same output. So we are squeezing together similar inputs. This is good because we capture a smoother and flatter manifold for our data by imposing these constraints. There is one drawback that contractive autoencoders have, is that computing this derivative here, so the derivative of the hidden representation with respect to the inputs, is fairly simple to compute if we only have one hidden layer, for example. But if we have a deep autoencoder with many hidden layers, this requires a lot of computations in order to compute all these derivatives. So if you have deep autoencoders, contractive autoencoders can be expensive to train, and sometimes they can be trained with by step, so one hidden layer at a time or something like that. But the outcome of this can be visualized here. So you have a more detailed description of this example in the textbook. But the idea is that we are representing here the derivatives of different neurons in the hidden representation with respect to all the inputs. So the input is an image, for example, this handwritten digit or this dog. This is a very small image, but it's a dog, at least according to the text. And we can compute the derivatives of these inputs, so of the output of the neuron with respect to each pixel, to each input. And this is a representation of the principal components of these derivatives. So where the derivatives point at the most. And we can see that when we are using contractive autoencoders, so when we impose that constraint of trying to minimize the derivative while still being able to reconstruct the data, the neurons will respond to some specific elements on the image. So, for example, with this 0, we have these kinds of parts of contrasts and so on the neurons respond to. With the dog, we also can see some parts of the shape. So the neurons are actually capturing something useful about the input. In comparison, if we do local PCA, if we try to find the principal components by doing principal component analysis, we get these kinds of shapes that don't really tell us much about the image. So they don't seem to be intelligently related to the image, so to speak. So contractive autoencoder is another way of obtaining useful features from our data. We can generalize a bit this. We've been seeing these deterministic autoencoders where we put in the examples and then we get some specific output here. But we can imagine that we can use the autoencoder to learn something that we can interpret as probabilities. This would be analogous to what we already do with classifiers. For example, if we have binary classification, we can output the sigmoid function and interpret that as a probability. With multi-class classification, we can use softmax and so on. So let's imagine that we are trying to obtain a conditional probability where the decoder is giving us some distribution for the x, which should be the same as the input, but the decoder is outputting that value as a function of the hidden representation. So here we could use some kind of distribution for the encoding or something like that. But let's think of this as the encoder giving us some probability distribution for the hidden representation based on the input, and then the decoder giving us some distribution for the values based on the hidden representation. So we could, in theory, use this to generate data. Let's think of how we could use this. We could train an autoencoder. The autoencoder converts this original image space into this latent space representation here in the midpoint. For the encoder part does this, and then the decoder goes back into the original image space. So this part just translates from the image data into the latent space. But if we could use this other part, the decoder, if we could feed in the right values here, we could use this to generate new images of this kind. So what we would need to do is to give it images that are part of this latent space where the images are represented. So basically, what we need here a bit more formally, we can create a discriminative model that tries to approximate some function of the output that we want conditioned on the input. This is what we do when we do a classifier. For example, we want the output of the classifier to be dependent on the input, and it will tell us this is class 1, class 2, or something like that, depending on the input that we give it. A generative model can be used as a discriminator too, but it approximates the joint distribution of the inputs and the target values. And then it can find the conditional distribution of the target based on the inputs, on the features, by this relation between the two. So if we have the joint distribution, we can use the marginal distribution of 1 and get the conditional distribution there. So this would be something like you're telling the neural network that this digit is of, say, the digit 8, and then the neural network outputs an image with the digit 8. So if your network can only do this, it's impossible to go back because you don't have the distribution of the actual features. You only have the conditional distribution of the class. It can tell you this is very probably number 8 based on the image that you give it, on the features. But with autoencoders, if we can decode from the hidden representation, then if we had an idea of the probability distribution for the hidden representation, we could actually sample from that distribution and then use the decoder to get the resulting data, the resulting image, for example, from this hidden representation. So actually, we would have the joint distribution of the two, we could compute it, and we would have a generative model. So how can we do that with autoencoders? We would need to know what the distribution of this latent space here is, so that we could pick a point inside the space where the cat images are encoded, in order that we feed this data, these values into the decoder, and the decoder gives us a cat image. The problem is that if we don't know the distribution of this latent space for the images, we can pick something that is outside these values, and then it will just give us trash, rubbish, noise, because it cannot map from outside that distribution. That's not what it learned to do. So if we fix the latent space with some distribution, then we could try to train the decoder in order to, from that particular distribution that we already fixed, it learns to output the correct answer, the correct image. This is what we can do with generative adversarial networks. We basically have two networks, one that receives random noise always with the same distribution and outputs images, and the other that receives a set of images generated by the first and a set of images that are of the kind that we want to reproduce, and learns to distinguish between the two. So it learns to distinguish the fake ones from the real ones. But now we train the two networks iteratively. So we train one, then the other, and train one and the other. And the generator is trying to fool the critic, the discriminator, and the critic is trying to tell the real images from the fake images. So by training both, we train this generator to map from our original predetermined distribution of random values, of hidden representations, into a set of targets that the discriminator cannot really tell apart from real images. And this works very well. So over the years, you have here the kind of progress of images generated for human faces. So these are all fake images. They are generated by generative adversarial networks, but they start looking pretty realistic and very good. So this is one way of generating data with these kinds of networks, by fixing the distribution of the latent representation and training the generator network to map from this distribution into something that is similar or similar enough to the target that it can fool a discriminant network. But we can do this with autoencoders. And one way of doing this is with variational autoencoders, where we train the autoencoder to encode into something that approximates a distribution that we want. For example, a mixture of independent Gaussians. And this way we learn the distribution, and we can sample from that distribution because we have the parameters. So without going into much detail on the formalities, let's think of the autoencoder as having this loss function. So basically this is the same loss function we've been talking about, but this is another way where you can see it expressed, which is we are trying to maximize the expected log probability of outputting the correct x based on some hidden representation here. Now I'm not calling it age as before, because this is not the actual values of the neurons, but it's something close to that. And since we are maximizing the log probability, and this is the loss function, we just put the minus there. But basically the idea is the same. Maximizing the probability of outputting that x, the correct x, based on something that is hidden inside our autoencoder. But we also add a penalty term here to the loss function, that is the divergence between what the encoder part is doing. So this Q, this P here is our decoder, this Q is our encoder. Our encoder is producing this hidden representation based on x, but we want this hidden representation to be close to some predetermined distribution. For example, independent Gaussians mixed together, something like that. That would be a common choice for this. So in this way, we are assuming that we have this parameterized distribution of the hidden representation based on x. This is our encoder that we are training. We are minimizing the reconstruction error that our decoder is obtaining based on the hidden representation the encoder created. But we also want to minimize this divergence between the distribution that we want and what we are getting from the encoder. Now the question here is, this is a bit tricky, how do we tell the difference between the distribution for our encoder and the one that we want? We would need to somehow evaluate the distribution of values in our encoder. And this would be hard to do, but what we can do is a trick here for variational autoencoders, where instead of measuring the distribution of the z that would be produced by our encoder, we train our encoder to give us the parameters of the probability distribution from which we are going to sample z. So instead of determining the actual encoding of our data, what the encoder is doing is determining the parameters of a distribution of probabilities that will generate the encoding of our data. And these parameters we can compare with that distribution and minimize the divergence. So this is the trick for variational autoencoders. We have this encoding here from which the cat image can be generated. So if we sample this encoding from the right distribution, we will generate different cat images out here. What we train the encoder to do is to compute the mean and standard deviations of the distributions, these Gaussian distributions, for each of the encoders. So if we have two values here that encode the image of the cat, we train the encoder to give us the mean and standard deviation for the first value and the mean and standard deviation for the second value. And now when we want to generate cats, we sample from these distributions and we get different cats. So this is how a variational autoencoder works. the tricky part here is to understand how we can backpropagate the error across this jump where we are generating data at random. So if we imagine that we are doing here this kind of thing, so we have the encoder gives us a mean and standard deviation, and then we draw at random a value from this distribution and carry on to the decoder. If then we measure the reconstruction error and want to come back with backpropagation, we get stuck here because we cannot backpropagate the derivatives if we have a random number being generated here. So we do this reparameterization trick. We have the encoder that is giving us the mean and the standard deviation, and the output for the decoder is the mean plus the standard deviation multiplied by a random variable, a random value drawn from a normal distribution with 0 mean and 1 standard deviation. Now, for this branch here, we cannot backpropagate because this one was picked at random and we cannot compute the derivatives of this random thing. But it's not a problem because we don't need to backpropagate here because we don't have parameters on this side. We only need to backpropagate through this standard deviation and the mean because this is what the encoder is learning. And these parts we can because the standard deviation, the derivative, is simply given by the product of whatever number came out there. And we have here a sum, so that's not a problem. So with this reparameterization trick, we can backpropagate through this step here where we are drawing at random from these distributions. And so with variational autoencoders, we learn probability distributions for the different values in the encoding, and then we can play with those and obtain different results. For example, this is a variational autoencoder trained on the MNIST dataset, on those handwritten digits, and there were two distributions here. So actually 4 values, mean, standard deviation, and each one determined a Gaussian distribution from which we can sample the different the values for the decoding. And these were learned for the different numbers. So we pass through many different numbers and we have combinations here of means and standard deviation for those particular numbers. And now we can combine them, and you can see that one of the neuron is determining which number we have. So if it's 0, 1, 2, 3, each one of these has different probability distributions on one neuron that determines the content. But then the other neuron is determining the style. So we have a number in the thinner line, in the thicker line, more in the diagonal, more in the vertical, things like that. So by changing different values into choosing different distributions on these neurons, we can combine different aspects of the numbers. The same thing for faces. So we can have one that determines which kind of person we have, and the other the kind of look in the glasses and beard and so on, and we can combine the different ones together. One good thing about variational autoencoders is that they learn to disentangle these different aspects of our data, and then we can use those to actually manipulate the data in ways that are meaningful for us. Now this I separated this into a different section, convolutional autoencoders, but they are not really a type of autoencoder that is fundamentally different. It's just that they are neural networks that have convolution layers throughout. So you can get images here and output images there. Actually, most of the examples I've been showing you were about this kind of autoencoders, but I'm just going to talk a bit about this part here where we use convolutions to upsample and reconstruct the image. Because last week we only saw convolutions doing this part, which was to convolution on the images to squeeze them down into fewer dimensions with pooling and things like that. So what we can do to get back to the original size or to even upsample some images and produce larger images is to use these deconvolutional layers. They are often called this. It's not a very good name, but there are actually several options that we can use for this. So we can use transposed convolution or shuffling after convolutions or perhaps the best way of doing this is to do upsampling and then convolution. So just quickly to give you an idea of what these are, this would be the convolution operation with one dimension. We have here our convolution kernel, these weights, that is sliding through the input. And then the output values would be this filter where we obtain, for example, this value here by multiplying this value by this part of the kernel, this one by this one, and so on, adding all these products, and then this would be the result. So as we slide the kernel through the input, we get the result of the convolution in this output. If we want to do it backwards, that is to say, in this case, we are shrinking the data into a smaller number of values because we are having this stride of 2 when we are sliding our kernel. If we want to do it backwards, we can do it like this. So we can imagine this would be the transposed convolution. We can imagine that we are sliding the kernel on our output here, and then we are adding to each value of our output the different values of the kernels multiplied by the input at different windows. So when we have the kernel here, we use the 3 multiplied by that input, and then we add this 1 multiplied by that input when we have the kernel on this position, and we keep sliding the kernel and building the output, which is something that is we can imagine it as transposing this kind of operation. Another way of doing this is to use this fractional stride convolution, where we imagine that we are sliding through the input in half a step increments, for example. So this is the actual input, and then there is some imaginary space there where we are simply ignoring that part. So when we slide the kernel from here to here, now we are only using this part of the kernel there on the input, or this value 2 and this value 4 on those two. But since we are ignoring these spacers here, we actually take a lot more steps to slide through the input, and we get something on the output that is larger than the input. So these are two ways that you can often find of doing these reverse convolutions, so to speak. A simpler way of imagining this, and one that actually works better, is to use upsampling, and then, for example, by copying the values and then simply doing a convolution on the upsampled layer. An alternative would be to do several convolutions and then shuffling. This would be conceptually a bit more complicated, but it does the same thing. So basically, this is the simplest way of doing this. You upsample your data and then apply a simple convolution to the result. And this works better than if you use transposed convolution or the other variants, which you can find in Keras, and in some papers you can find them being used. But since they have these different overlaps as we slide the kernel, they tend to generate these kinds of artifacts on the images generated. Whereas if you just do upsampling and then convolution, you don't get these kinds of artifacts. So basically, if you want to work with images, this is just an idea of how you can go from the encoding, which tends to be smaller, back into a real size, the original size image. One example of doing this, of using these convolutional autoencoders and also solving that problem of estimating the distribution of our hidden layer, is to share the latent space. So just to go quickly by with this example, this is for deepfakes. We train one encoder with distorted images of Jimmy Fallon in this case and John Oliver. So we are adding noise to the input images, using the encoder to build a latent space representation, and then we have a decoder for Jimmy Fallon to obtain the image back. We do the same thing with John Oliver with the same encoder, but we use a different decoder so that we can again get the real image of John Oliver back after inputting a distorted image. So the trick here is that since this is the same encoder being trained for both decoding tasks, The latent space representation for images of Jimmy Fallon and John Oliver is shared. It has the same kind of encoding, does the same, captures the same kind of features. The thing is that we use one decoder to get Jimmy Fallon here and another to get John Oliver. But we can switch the decoders, and since the latent space representation is the same, we can generate images of John Oliver from images of Jimmy Fallon if we encode with the encoder and then decode with John Oliver's encoder. And this you can do this kind of swapping on the images by automatically switching one face for the other. So, as you can tell by the length of this lecture, autoencoders are some of my favorite kinds of networks. And the basic idea is that we can train the network to learn to replicate the input in the output, so it works in an unsupervised way. But by imposing some restrictions, we can get it to do interesting things, like rebuilding data from corrupted inputs, like finding the best features, like giving us distributions to generate data, and so on. So I recommend that you read chapter 14 of the book for the autoencoders. And although for generative models, you're going to talk a bit more about them later on in the semester with Professor Rui Rodrigues. But for this part, I talked just about in the context of autoencoders. So I already talked too much over my time. We're going to take a 10-minute break. We'll continue at 5:15.